Thanks, Sammy. I'm glad to be here. MC10 is a venture-backed company based in Cambridge, Mass. And I'm going to talk a little bit about stretchable and conformal electronics on the human body, trying to take electronics into new places and, in particular, apply them to soft tissue on the skin, inside lumens in the body, and try to give you a few examples of what that looks like. So the problem we're trying to solve is that conventional microelectronics are rigid, brittle, and planar. There's a $300 billion industry that's grown rapidly since the invention of the IC 50 years ago. Moore's law has been great for making things smaller, cheaper, and faster. But the issue is that everything's in a rigid box. And the natural world and human beings in particular are not particularly planar. And we're not 19-inch racks that can take a board slotted into us. So we're trying to do some new things with electronics, put them onto balloon catheters, be able to twist, stretch, bend, expand microelectronics, and use them in novel applications. The technology is a spin out of the University of Illinois. It's been published in lots of very cool scientific journals, on the cover of a lot of them in many different applications. It's also gotten some popular press because of the notion that you can extend a big base of investment over many years and innovate in a new direction. Instead of just making things smaller, cheaper, and faster, we can instead deploy them in radically new form factors that interface well with the human body. So the first insight is really that if you have something that is thick, it's very hard to move. If you make it thin, you can make it flexible, right? So think of the difference between a 2x4 and a piece of paper, or a sheet of plate glass and a fiber optic cable. Same fundamental material, very different mechanical properties. So what if you do the same type of thing with silicon-based microelectronics? That's essentially what we're doing. We take a mesh of electronics. We have thin islands which house the solid-state devices. We put springy interconnects in between, much like a slinky, and then interface it onto a thin, conformal polymer. So think about stickers or decals or saran wrap-like electronics that still have the power of the microelectronics that are in your smartphone. And if we think then about how we apply it to the types of problems we talk about in wireless health and connected or body computing, I think one of the critical things is to have a system solution that works together and that is super simple at the end of the day for people to implement. And we've heard a lot this afternoon about some of the various aspects of that problem. The wireless connectivity, the data analytics to make sense out of all the data and to come up with a simple, actionable result that a user can deploy. We see relatively little happening on the very front end, what we call seamless sensing. And that's really something we're focused on at MC10. And if you think about what it takes to make sensing seamless, there are really three aspects of it. One is you don't want to sacrifice in the quality of the data. So being able to use high-performance devices, having them interface directly with the body, not have motion artifacts and noise as you're moving around or going about your normal life is really important. So you don't want to sacrifice much on the inputs. You want to make it super easy to use, something that is invisible to the user. It's part of your everyday life, and particularly, if you look at populations, the aging population that may not be as tech savvy, you want it to be super simple. The last piece is it needs to be scalable. So it needs to be cost effective. It needs to be based on standard manufacturing infrastructure for microelectronics that's already out there. And that's what we try to capitalize on with MC10's technology. So we're trying to move devices that are smaller than they used to be, but still rigid and boxy, and take those into thin, conformal formats in what we call seamless sensing. So, the first place I'd like to start is, imagine a smart sensing sticker. We call this the biostamp. It's something that's extremely thin, extremely light. It's matched to the stretchiness of the skin, so you can see when you pinch it, it's a lot like a kid's fake tattoo. It really moves with the body. And there are lots of different things you can do with this. We published some of this work in Science last summer, and there are a variety of different vital signs that you can measure on the body. But just to touch on a few different applications, you can imagine a device that's worn by a child so you know his activity level or location. You can imagine a patient with congestive heart failure where you want to monitor the contractility of the heart and know if someone's taking their meds appropriately. You could imagine applications in sports where you're trying to measure the impulse to the head and see if somebody needs to be checked out for a potential concussion. A diabetic that has a sensing sticker that could be an early indicator of hypoglycemia, et cetera, et cetera. There are lots of different potential applications that we could certainly talk about, and maybe we'll talk about a little bit later. If you can run the video back there, maybe a real simple example to capture what the type of thing we're talking about. Every parent has had a sick child, and there's nothing more terrifying than going to bed at night wondering if your child is going to have problems breathing or if he or she has a extremely high temperature. Imagine having just a simple sticker that can monitor temperature and respiration and alert you if something's going awry. So that's the type of example that happens in the background, is fairly simple to comprehend and to to use in a broad deployable way. So that's one of the areas where we're focused. Just briefly, we've also looked at other minimally invasive and implantable applications for conformal electronics. We've done a lot of work with catheter-based electronics as well as sensor sheets that go in and on soft tissue in the body. So from things like looking at atrial fibrillation, renal denervation, assessing what's happening inside lumens, whether a stent is necessary, so FFR, looking at TAVI, a lot of different potential applications we don't have time to talk about, and could still leverage the same type of wireless capabilities that are in the biostamp type device. So just conclude by saying that we think that reshaping electronics will change medicine and help advance the quality of life. Clearly, we're not going to do this all on our own, and it's really important for us to work with others that are doing the wireless connectivity and some of the data analytics, and you'll hear from some of those here on the panel this afternoon. So thanks for your time.
Yeah.